Faraday's law says that if you have a changing B field, or if through a closed area, if you have the flux changing as a function of time, it is going to induce some EMF, something like a voltage along that loop. Also, if you have a changing magnetic field, you're going to create E field. And this kind of E field is different from the E field created by charges. This kind of E field, they can form loops. So if you integrate those induced E field along a closed loop, you're going to get non-zero value if the B field is changing in that area. And then the flux through the region is going to change as a function of time, and the time derivative is not zero. These two equations, essentially, they are talking about the same thing, but this does not rely on a real physical circuit or loop. And it describes the BE field, which can be induced whenever your B field is changing. And this is the same idea, but it relies on a physical actual circuit. And the circuit can have actually not only one turn, it can have more than one, it can have n turns. The total accumulated EMF induced in the circuit is equal to n times of that. And the flux, again, the flux is defined to be the number of magnetic field lines penetrating a certain area. And that is equal to B, the B field, dot product the normal direction of that surface, and then integrating small patches of A. If the B field is uniform, it may even still have an angle comparing to the normal direction of the area. Still, if the B field is uniform, we can take it out of the integral, and this flux calculation becomes simply the B field. If your surface area is flat, then it becomes B field multiplied area, and the angle between the uniform B field and the flat surface it's going to be fixed. And if we choose the angle to be the angle between the B field and the normal direction of the surface, and that's going to give you a cosine theta. If you have a B field into the page, and you have your surface parallel to the page, and then the normal direction and the B field are in the same direction, the flux equal to B multiply that area, multiply cosine 0, which is 1. If your B field is into the page and your area is like this, the normal direction and the B field direction are perpendicular to each other, in that case, cosine 90 degree give you 0. You have no flux if your B field is into the page and your surface is parallel to the B field. Or if you are at an angle, then basically you just use the cosine of the angle between your B field and the normal direction of your surface. And that's the angle theta here. So let's use two examples to apply Faraday's law. First is that if in a circular region, we have a uniform B field. However, this B field is changing as a function of time. This can be any type of a format, sine, cosine, linear, increasing or decreasing with time, or any other function of time. Anyways, it's a B field changing as a function of time, and we know that's going to induce some E field. And the E field is going to be looping. And at location P, we try to find out the induced E field. And because this region is circularly symmetric, we can imagine choosing a circular loop for Faraday's law. And this circular loop has a radius r equals to the distance from the center to location P. And then this is your loop. Okay, along this loop, we can figure out the E field. And also notice this negative sign. The negative sign says that the induced E field or induced EMF always try to go against the change. It does not like change. So now, if the B field increases, this function is a B field increases with time. And then the flux going through this region, flux is equal to the B multiplied area. Now, the B is perpendicular to the area. B is parallel to the normal direction of the area. Cosine 0 equal to 1. So simply flux equal to that. If B is increasing with time, area is not changing, we know the phi B is also increasing. If the phi B is increasing and also it's into the page, then we know the induced B field will go against that, so the induced B field will be opposite, will be out of page. So what can give you an induced B field out of page? Imagine current flow in what direction is going to give you an induced B field out of page. Using our right-hand rule number 3, we see that if our induced E field, or you can imagine current flowing counterclockwise this way, we are going to get induced B field canceling out the increasing initial B field. That means the induced E or current. I put a quotation mark here because we do not really have a current. We do not really have wires. Imagine if we have a wire, that's what the current is going to be. But that's the direction of the induced E field. It's going to be counterclockwise. Okay? And then we can further solve this problem by looking at this equation. And then for this loop, we have the E field ds. Because the E field and the ds is the same direction everywhere, this integral for the closed loop give us E multiply integration of the total amount of ds, which is 2 pi r, okay? And that's equal to d phi b dt, which is negative d phi is b and the area dt. And this area is simply not changing as a function of time. So you can take area out, that's negative sign, dB dt. Also, the area is equal to pi r squared. Now, the amount of area which provides us the flux is the same area, like has the same radius like this integration loop. So they have the same r. So this is the E field multiplying the circumference equals to the negative sign of the area multiply dB dt. If you know the function of B as a function, if you know B as a function of t, you can find out the dB dt, and then you can solve for the induced E field, and you know that's in the counterclockwise direction. Similarly, we can also do something here. If we have a conducting wire arranged this way, and then we have another conducting wire touching that, but moving with a velocity, constant velocity v in that direction. What's going to happen is that, let's look at the flux. The flux actually B equals to B multiply area, uniform B field into the page multiply this area. And if this is 0, this is location x, and that's moving toward the x direction, okay? So, and if this is the length, it's L, so it's B multiply area, and the cosine 0 degree give you 1, the total flux, it's that without any extra angle, and that's equal to B multiply L multiply x. So now let's take out dB d phi dt. How does the flux change as a function of time, which is dBLx. B is not changing, it's uniform constant. So here we have a constant B. But what is changing? Because this while it's moving, the area of this loop is changing. A is changing. This constant L is constant. So the only thing changing is x. So we have a B, L, and dx dt, which is B, L multiply the speed, velocity. Okay, that's d phi b dt, and that's going to be equal to the amount of EMF induced inside. The absolute value of that equals to d phi b dt absolute value, which is equal to BLV. But in which direction? Because this area is increasing, we are having more flux into the page, and the induced B field is going to be out of page. The induced current is going to be counterclockwise, like we just did before. So we have a current going this way, and this way, and this way. So as if we are generating a battery, which is in this direction, which has battery voltage equal to BLV, and that's in this circuit. If you here you have a resistor, and then you can generate a current, okay? And also, if you have a resistor R, and then you have Induction over.
Again, the main library will be closing in 30 minutes.
We are going to have a current I equals to the epsilon over R if you have a resistor here. And then correspondingly, you know, the power generated here or used here is equal to I epsilon, which is equal to epsilon square over R, which is determined by the B field strength, the length of the wire, the speed, and that square over the resistor. And also, when the energy is consumed inside this wire, somebody pulling this wire to move this way to maintain a constant speed has to do some work. Okay, and that's the examples of Faraday's law. Basically, the idea is that whenever you have a changing B field, even though your area and nothing else does not change, or even if you do not really have a loop of circuit, you are going to generate a E field, which is looping. And that E field can be calculated using this equation, while you choose the appropriate loop and simplify this integral, and then calculate the derivative of flux versus time. And if you do have a real circuit, and then you can change the flux going through that loop by either changing the area like this, or you can change the B field, make it stronger or lower by controlling the external B field, or you can also change the angle theta. You have a fixed B field, you have a fixed loop, but by rotating it inside the B field, you can change the flux, and then your d phi dt is not zero, you induce some voltage in your loop. And that's exactly how the electricity that we are using in the city are generated.